Hello everyone. Have you ever looked up at the bright blue sky on a sunny day and wondered, why is it blue? Or perhaps you've admired those stunning red and orange hues painting the sky during sunrise or sunset and asked yourself, why does the sky change colors like this? Well, the answer lies in a fascinating biological and physical process called light scattering happening right above us in Earth's atmosphere. You see, sunlight is white light made up of many colors, each with different wavelengths. When this sunlight hits the tiny gas molecules and particles in the air, mostly nitrogen and oxygen, it doesn't just pass through, it scatters. But here's the interesting part: shorter wavelengths of light, like blue, scatter much more than the longer wavelengths, like red. Because blue light has a shorter wavelength, it scatters widely across the sky when the sun is high during the day, giving us that beautiful blue canopy overhead. But during sunrise and sunset, sunlight has to travel through a thicker layer of the atmosphere. This longer journey causes the blue light to scatter out of our line of sight, allowing the longer red and orange wavelengths to become the stars of the show, painting the horizon with those rich, warm colors. So the next time you watch a sunset, remember, those vivid reds and oranges are the direct consequence of how Earth's atmospheric particles scatter sunlight differently based on wavelength. Nature's own beautiful canvas comes alive thanks to this amazing interaction of light and life. Welcome back. Now, let's dive a little deeper into the science behind why the sky is blue and sunsets are red. This phenomenon is caused by something called Rayleigh scattering, named after the scientist Lord Rayleigh. Rayleigh scattering occurs when sunlight interacts with particles much smaller than the wavelength of light, think tiny gas molecules in our atmosphere. The key here is that the intensity of this scattering is inversely proportional to the fourth power of the wavelength. That's a fancy way of saying, the shorter the wavelength, the more it scatters. Blue light, having a shorter wavelength, scatters far more than red, which is why the sky looks blue. Mathematically, we write this as scattering intensity proportional to 1 divided by lambda raised to the fourth power, lambda being the wavelength. This explains an interesting detail: violet light has an even shorter wavelength than blue, so it should scatter the most. But here's why we don't see a violet sky. Our eyes are more sensitive to blue light than violet, and also, much of the violet gets absorbed by the upper atmosphere. This biological sensitivity combined with atmospheric absorption means we perceive a blue sky instead of a purple one. Understanding this mechanism is not just about sky colors, it also helps us grasp how light penetrates the atmosphere and affects biological systems on Earth, a beautiful confluence of physics and biology. Hello again. Have you ever noticed how difficult it is to see clearly on foggy days or in smoky, polluted cities? This reduced visibility happens because of increased scattering of light caused by those tiny water droplets in fog or particles of smoke in the air. Unlike Rayleigh scattering, which involves very tiny particles, fog and smoke droplets are about the same size as the wavelengths of visible light. This causes what we call Mie scattering, where all wavelengths, red, green, blue, scatter almost equally. That's why fog appears whitish or gray and obscures the view. This diffuse scattering of light is why car headlights often become less effective at night in fog. Have you ever noticed cars using yellow fog lights? That's no accident. Yellow and red lights have longer wavelengths, which scatter less in fog, allowing them to penetrate better and improve visibility. So, the next time you're driving through fog or walking in the city on a smoggy day, remember, the physics of light scattering is playing a crucial role in what you see and how safely you can drive. Hello explorers. Have you ever wondered why the sky doesn't look the same on other planets? The answer lies in their unique atmospheres and how light scatters within them. Take Mars, for example. its sky has a reddish or salmon pink tint. This is because its atmosphere is filled with very fine dust particles rich in iron oxide, think rust. These dust particles scatter sunlight differently from Earth's nitrogen-oxygen air. The Martian atmosphere is thin and doesn't produce much Rayleigh scattering. Instead, Mie scattering by dust dominates, giving the sky its distinctive reddish color. Now, consider Venus wrapped in thick clouds of sulfuric acid. Here, light struggles to penetrate at all because scattering, along with absorption, works differently, making the visible sunlight barely reach the planet's surface. These differences in atmospheric scattering don't just affect how the sky looks, they also influence any potential life form's vision and sensing. For instance, if life ever exists or evolves in Martian-like environments, their eyes might be tuned to detect longer wavelengths to make the most of their reddish skies. So planetary skies teach us how life and light dance together beautifully, guided by the environment's peculiarities. Welcome back. Have you ever walked into a dusty room and suddenly noticed beams of sunlight streaming through, making the dust particles glow in the air? This fascinating effect is called the Tyndall effect, and it's another beautiful example of light scattering. The Tyndall effect occurs in colloidal systems where particles are large enough to scatter light but small enough to remain dispersed. When a beam of light hits such particles, it scatters in all directions, making the light's path visible. You've surely seen this when mist scatters the light from car headlights or during science demonstrations with lasers shining through milky water. In biology, this scattering helps scientists study cell suspensions and detect tiny particles like proteins or pathogens in solutions by observing how light behaves. A simple yet classic experiment is shining a laser through milk diluted in water. Watch how the tiny fat particles scatter the light, clearly revealing the beam path, a perfect example of biology and physics combining to reveal the hidden world. Hello scientists! Did you know that the scattering of light inside your very own eye can affect how clearly you see the world? In healthy eyes, the cornea and lens are transparent structures that minimize scattering so that light focuses properly on the retina. But in conditions like cataracts, proteins build up in the lens, increasing light scattering and causing blurred or hazy vision. Medical technology takes advantage of scattering principles too. Optical coherence tomography, or OCTOBR, uses scattered near-infrared light to create detailed images of the eye's internal structures, helping doctors detect retinal disorders early. Beyond the eye, scattering helps in biological imaging techniques such as confocal microscopy and flow cytometry. Even the tear film on the eye's surface can scatter light when irregular, leading to visual distortions common in dry eye syndrome. So, understanding light scattering isn't just about the sky or fog, it's embedded in how our bodies function and how medicine advances to keep our vision sharp. Alright, let's wrap up today's exciting journey. We started by uncovering why our sky is blue and sunsets turn fiery red, all thanks to how light scatters in the atmosphere. We saw that Rayleigh scattering governs our daily sky color, while Mie scattering explains the foggy, whitish haze and the peculiar colors on other planets. We also explored how light scattering is crucial inside your eyes and in cutting-edge medical devices that help us see better and diagnose illnesses. From the natural beauty of dawn and dusk to the microscopic vision inside our bodies, understanding the different types and causes of light scattering connects physics firmly to biology. Remember, the vibrant and colorful world you see is painted each moment by the invisible dance of light interacting with matter, nature's own painter's brush. I hope this session opened your eyes to the amazing biological and physical processes happening all around and within you. Biology truly is the science of life in all its incredible complexity and beauty. See you next time as we explore more fascinating secrets of the living world.